Right, this is question 5. And we've got a mass on a spring, a classic sort of SHM setup. The 3 springs are identical. Okay, and this setup with a single mass on a single spring, this setup with 2 masses on 2 springs. Yeah, on the left, T1 is the sort of time period for oscillations, and T2 is the one on the right, and we're after the ratio. So I've got the data booklet right here, so I can just remind myself, if necessary, of that time period equation. It is T equals 2 pi root m over k. It's this one at the bottom there. I don't know if you, I don't think you can see my mouse pointer, so I'll highlight it. It is that one. T equals 2 pi times the square root of m over k. So 2 springs in series like this, if you apply a mass to them, they'll both stretch by the amount that this one would. So the total extension is twice as much for a given mass. Therefore, the spring constant is half. So it does say give your reasoning. So I'll just state that 2 springs in series has spring constant k over 2. Half the spring constant because half as much force for a given stretch or whatever. So given that T1 is equal to 2 pi root square root over k, then T2 has twice the mass as well, is 2 pi square root 2m over k over 2, which is equal to 2 pi square root 4 over k. So we're after the ratio T2 over T1. These expressions are the same except for this 4 in the mix, and it's inside the square root. So that is equal to 2 times 2 pi root over k, which of course is T1. 2 times T1. So T2 over T1 is just equal to 2. And that's it. I think this is probably, it says giving your reasoning. I think this statement and sort of identifying the right equation from the formula sheet, I think that's all we're going to need for that. Okay, moving on to part B. Be really careful in stuff like this. Look, it says a separate experiment. So we're no longer dealing with this sim spring system. We've got a mass hanging from a spring is displaced upwards by 30 millimeters and released, so performs simple harmonic motion. So classic SHM setup here. We're given the time period. Show that the maximum velocity of the mass is approximately 0.16 meters per second. So here is on the formula sheet, here's the equation for velocity. So I can just write that in. Velocity is equal to minus a omega sine omega t plus epsilon. This is based on cosine for the displacement, and a cosine of course starts at maximum. Cosine starts at maximum amplitude, maximum displacement at t equals 0, and that is what's happening here. So we don't need any phase constant, we don't need any add-on to this. So that is just 0. So the max value of the sine function, it actually doesn't matter whether it is or it isn't. The maximum value of the sine function is 1. So is just a omega, and of course omega is equal to 2 pi over t. Sorry about my handwriting, that's atrocious. Omega is 2 pi over t, Therefore, Vmax must be equal to A, the amplitude. Just be careful with units. Multiplied by omega 2 pi over 1.2. Chuck that in the calculator and get 0.157 meters per second, which is approximately 0.16. Job done. Okay, sketch a velocity time graph on the grid provided. So the information we need is back here, isn't it? We've got a time period of 1.2 seconds. We've got a maximum value of 0.16, and we know that there was no phase constant necessary to add on because this was released from 30 millimeters upwards at time t equals 0, 30 millimeters upwards. So its initial motion is going to be downwards. It's going to fall downwards. So it's going to start from its point of release, fall, accelerate downwards, and then, so it's, as suggested here by the equation, it's a minus sign function is what I'm trying to draw. But I will need to get stuff right, so let's just be a little bit careful. That's 1.5, so that's 1.1, 1.2. So that's the time period, and the amplitude was 0.16. So where is that? 0.16 is there. 0.16 negative is there. So I need something that's going to basically do, this is going to be really ropey, me attempting to draw this is going to be very poor indeed, I suspect. It's going to cross this point and it's going to look something like, oh lordy, it's bad. Really tricky drawing with one of these. Oh my goodness, that is horrific. Maybe if I just go for it more confidently. No. I'm making this look harder than it really is. But those are the important points. Surely, we've got like the maximum. We know that it's a minus sign. We know its time period. We know its peak values. So I don't know. I'm going to stop drawing that anyway. Yeah. Anyway, that's that, isn't it? It's a minus sign. Calculate the speed of the mass at this time. No problem here. We just use our equation from the formula sheet, and we've got a time to fill in. So V is going to be equal to minus A omega sine omega t. So minus 30 millimeters is the amplitude, times omega is 2 pi over t, 2 pi over 1.2 multiplied by the sine of 2 pi over 1.2 times 3.5, and chuck it all in the calculator. Oh, my calculator app's gone to sleep. Sorry about this. Make sure, of course, when you're doing stuff like this, that you are in radians. Don't be that person. Not 0.079 meters per second. Okay, and that's actually a positive. So it says speed. It says speed, so we don't actually have to give a direction. So there's no problem there at all. So I'm just going to leave it as that. Always be careful questions like that with your direction. I think if it asks for a velocity, it is always best to give a positive speed and state a direction in words. Okay, Ursula claims, or thinks rather, that the kinetic energy varies at a frequency of 1.67 hertz value at this claim. So kinetic energy is proportional to V squared, proportional to velocity squared. Because it's a square, the kinetic energy is maximum twice in a cycle. So therefore it has twice the frequency. The kinetic energy varies with twice the frequency of velocity. So 2 times the frequency of the velocity, which is 1 over t. Yeah, 2 over 1.2, and 2 over 1.2 is 1.67. I shouldn't have needed a calculator for that, should I? Yeah, so she is correct. Okay. No, there's more. Ursula modified the mass spring system so that its oscillations are significantly damped. Suggest what practical modifications she might have made. This is a practical that you may well have done. When you want damped oscillations, you're looking to increase the resistive force. So I would suggest add some thin card to the mass to increase our resistance. I think that's a pretty standard sort of practical where you stick a bit of card in between the masses on the hanger to, oh, not resistor, resistance, sorry, to increase the air resistance and damp your oscillations. And so these are damped oscillations that we're looking at here. Evaluate whether these are consistent with an exponential decay of amplitude. So in general with damped oscillations, this is the type of expression you can write for amplitude. And this is the same as the expression that you have in radioactive decay, in the sort of decay of, or rather the decrease of charge stored in the capacitor, those types of things. Exponential decays imply that the fractional change in a given amount of time is constant. So whether it's a half-life or whatever, you know, it halves and then it halves and then it halves. It doesn't have to be a half-life. You know, if you think of capacitors, the time constant is how long it takes to drop by 63%. So if we can show that these fractional changes are the same, then we should be away. In whatever unit of time. So let's do it. 24 over 30 equals, and then 19 over 24 equals, and then I haven't really left myself enough room. 15 over 19 equals. So sorry, let me just chunk those into the calculator. 0.8, 0.79, and 0.79. So yes, that is consistent with exponential decay. Just write something all roughly equal. I don't know what's going on with my spelling. All roughly equal. So consistent, something like that. There's other ways you could do this. You could take the log of the change and yeah, but I don't know about that. But yeah, or you could even work out sort of lambda t and show that 30 times e to the minus x. If 30 times e to the minus x is 24, you could find x and then show that 30 times e to the minus 2x is 19 and 30 times e to the minus 3x is 15. You could do it like that and get the same result. Okay, final part. The physics of damping has been used in car suspension and suspension bridges. Compare the purposes in bold. Purposes that damping serves in these two cases. So car suspension, what does the damping in car suspension do? It sort of prevents the car from continuing to oscillate after you go over a bump, and just, you know, so it takes energy out of the system, I suppose. Takes energy from system, so prevents cars from oscillating, really, and like a mass on a spring after bumps, after driving over a bump, something like that. Whereas in a bridge, I mean, I'm sure everybody's seen the video of sort of Tacoma Narrows, the bridge that collapsed. Bridge damping sort of famously is put in place so that the bridge doesn't experience resonance. So in bridges, it's there to reduce the, again, it removes energy. And it lowers the amplitude of the kind of swaying. I'm not really sure what they want here for 3 marks, so, you know, I've just basically described what damping does in a car, and I've described what it does in a bridge to reduce the amplitude of swaying. It says compare the purposes, so I guess I'll say in both cases increases safety, because it would be pretty dangerous to be driving an oscillating car, wouldn't it? And walking on a swaying bridge or driving on a swaying bridge is pretty dangerous too. And hopefully that gets my 3 marks. I'm thinking sort of 1 for describing what it does in a car, 1 for describing what it does in a bridge, and then 1 for the comparison, maybe. Anyway, that's question 5.